Hey, it's Tony from Adafruit, and in this video we're going to look at how to do a holiday light project, the smart holiday lights with MicroPython. And I say smart holiday lights because like every smart gadget, this has to be something that's controlled through your phone or through a web page. Basically go to a web page and change the color of lights that are on like a Christmas tree or a wreath or decorations or things like that. So kind of a fun holiday project. And it'll be interesting to try to do this with MicroPython, and specifically the ESP8266 version of it, because with that little Wi-Fi microcontroller, it's really easy to access the web and use things like web technologies, and it has like the web REPL built into it. So it'll give us really easy access to put it onto our Wi-Fi network and then control the color and the animation of the lights with it. So let's just kind of dive in real quick and we'll get started with it. This will actually be probably part one of what will probably be maybe two parts, maybe three parts at the most, but probably just two parts in this little mini series on the Smart Holiday Light project. So in this first part, we're just going to look at how to do the animation code and some of the basic kind of usage with like how to light up the NeoPixels, how to animate them with MicroPython. And then in the second video, I think we'll dive more into how to make it a smart project so that I can control it from a web page. You know, right now with this example, I can show you how to use the web REPL to control it through the little web interface that the ESP8266 gives you. But in the next video, I think we'll look at how to make like a nice little web page with a button that you can click, or maybe colors that you can select to send to the strand of lights to animate them. So let's take a quick look at what we want to do eventually. Well, I guess here I'll stay in this main view. So ultimately, this is what I was thinking, and I'm not going to do this yet in the project. Oh, you can see the cat. She's quite interested in this wreath. So this is my ideas. You know, you have a little holiday decoration like a wreath or something like this, and then you have something like, let me grab this, something like this. So this is a big set of, this is about 4 meters of NeoPixels. So just the addressable RGB LEDs, this little strand right here you can see has a whole bunch of NeoPixels on it. So this is the easiest holiday light project in the world, that you can just wrap these lights around a wreath, for example. You can wrap these around a Christmas tree, anything really, any kind of decoration. You could, you know, trim a window with these to light up your windows, whatever you want to do with it. But ultimately what we want to do is control the color and the animation of these lights right here with MicroPython. And so that's what we'll kind of dive in. And I'm not going to do this first video using this wreath and these lights. I'm actually just going to use a little NeoPixel shield. Oh, my cat is quite interested in this wreath. But I'm just going to use a NeoPixel shield, so it'll be a little bit easier, because if you can light up a small little NeoPixel shield, then you can light up a long string of NeoPixels just by changing the number of pixels basically for this. So let me put this wreath away in a spot that the cat is not going to get to it. She is eyeing up this wreath. Maybe if I put it under here, maybe that will, you know, if she can't see it, she can't get to it, hopefully. So, okay, so like I said, we're actually just going to get started with a much smaller thing, and I'll jump to the main view real fast. Let's go to the desktop view. So, okay, so in the upper right-hand corner, you can see right here, this is actually the ESP8266 Feather Huzzah. Let me pull that off. So you can see under here, this is the ESP8266 Feather Huzzah. Basically, the ESP8266 little Wi-Fi microcontroller module runs MicroPython super well, very easy, very nice and stable, and it has Wi-Fi access, so you can put on your Wi-Fi network, and that's how I'm going to make this a smart project, because with a Wi-Fi connected microcontroller, I can go and talk to it from a web page. And then this little thing right here is the NeoPixel Feather Wing. And so this has a little grid of 4 by 8 NeoPixels. So that's 32 pixels total. And it's just, you know, nice. This is effectively one strip of pixels. So like there's an input, the pixel I think starts up here and then goes all the way down in a strip to the bottom, the end pixel here. So it's really no different than this big set of pixels that I have right here. This is like 4 meters of pixels. Exact same thing here. You know, each of these pixels works by just being serially connected. You know, the first pixel is connected to the next pixel, and it just sends the color data on down the chain. So this little, I can prototype on this little feather wing, and then when I finally take the real code to the wreath or the Christmas tree or whatever you want to do, then it'll be pretty easy, because I just need to change, okay, with this strip of pixels, I might have like maybe 300 pixels in it, whereas this little shield, I only have 32. So it's a little bit easier and faster to prototype with. So like I said, this is ESP8266. Make sure you're running the MicroPython on here, and I'll talk a little bit more about how to do that. But look in the video description when this goes up on YouTube, and I'll put a link to some of the earlier guides that I've done that show you how to load MicroPython onto a board, especially the ESP8266, how to get that loaded and get the latest version on there. Now, let's see, one thing real fast that I'll show you. So the inspiration for this project, or what I'm going to use as basically a building block for this project, is an earlier project that I did called the Techno Tiki Torch. And I'll put a link in the description when this goes up on YouTube. Look below and you can see a link to this project. But basically, this is a little project I made to make a neat little animated light display. The idea was, you go camping out in the summer and you might want to set up some cool decorations like around the tent or something, or even just out in your backyard or whatever. And I found that if you took a mason jar like this and filled it with some like clear glass kind of vase filler material, just little glass beads basically, then that would diffuse whatever light is inside of there and make it kind of glow. And so if you put like a little strip of NeoPixels inside of there, and I think I used a Gemma microcontroller in this project, then I could just animate those NeoPixels. And let's see, if I play this video, it'll probably, let me turn off the sound, but you can kind of see like, okay, yeah, so it's basically just doing some little animations, like it's changing between colors right here. This one's changing between a different set of colors. I think I even had a version of the Techno Tiki Torch that had an infrared remote control receiver connected to it, so you could use a little infrared remote control to change the animation and the colors, which works really well for maybe a non-smart project where you're just using, the old-fashioned remote control. Who wants that? Nowadays, the smart projects, you have to use your phone. So you can see in this video, I was just showing the little infrared remote control. So that's what I want to eventually do with this holiday light project, is make it so that your phone can basically control these animations by maybe opening a web page and getting a little UI, a little interface that says, okay, here is your smart Christmas wreath or Christmas tree or holiday tree or whatever you're doing. And then what color do you want? So you can maybe pick like a range of colors. What's the speed of the animation that you want? What type of animation do you want? So in the Techno Tiki project, I had a couple different animation types. I think I had one where I just lit all of the colors, all of the pixels the same color, and I would just transition between a whole set of colors. So it would just loop through a list of colors, changing all of the pixels to that color. And then I think I had a second type of animation where it would do like a theater chase, where the first pixel gets the first color, the second pixel gets the second color in the list, and so forth all the way through the list, and then it just moves that color set along all your pixels. So it looks like if you had 3 or 4 colors, it's just that set of colors moving along your line of pixels. It's a little bit easier once you see it to understand kind of what it means. But I figure that's what I'll start with in this video, is we'll just do the basics of how to recreate those effects in MicroPython. And then in the next video, we'll look at how to actually make this smart and something that I can control from a web page. And I have some interesting ideas. I haven't actually gone through and done all the implementation of it yet, but I think we can use the little WebSocket listener that the MicroPython ESP8266 port uses, so that it might make it a little bit easier for us to control this from either the web REPL or from this little web page that we create that uses the WebSocket connection. But more on that in the next video. Okay, so let's kind of dive in here. Now, like I said, you do need to make sure you're running the latest version of MicroPython on your ESP8266. I'm running the 1.8.5 version, and I'll put a link right here. This is the micropython.org website. I tried 1.8.6, but for some reason on this board, when I load it up, it doesn't work. It just spews a bunch of junk. I erased the flash memory. I'm still having issues with it. So if you see weird behavior with 1.8.6, try downgrading to 1.8.5 and see if that maybe works for you a little better. It could be, who knows, some kind of a bug. Again, MicroPython's still pretty new, so there's all kinds of little issues and things that people are sorting out. Okay, so let's just dive into the code right here. So I'm just going to start hacking away on some of the code. Like I said, if you're totally new to MicroPython, I'll put a link to a What is MicroPython guide in the description below. Start there. That explains a little bit more. In this video, I assume that you have a little more knowledge about MicroPython. Okay, so let's just get started. And maybe the first thing I'll do is I'll connect to the web REPL on this board. Now, also a note, if you do manage to use the latest 1.8.6 version of MicroPython, they disabled the web REPL by default. So when you load this firmware firmware, the web REPL is disabled. I believe you need to look at the release notes to see how to enable it again. But really, ultimately, I guess I'll show you. So in your boot.py, that's where you can enable or disable the web REPL. So if you want to edit that file, and I'll use the AMPI tool, which I've shown in a bunch of videos and I mentioned in the tutorials that I'll link to in the YouTube description below. AMPI is a little tool that I created to get and send files to a MicroPython board. So for this board, I have it plugged into my computer, and it shows up as a serial port. On the Mac, it's like the /dev/tty.slab USB to UART device. So with AMPI, what I can do is I can say AMPI, give it the port option and the port of my board, and I can say just ls, just list the files on this board. And so you can see there are a couple files here, and then if I run the get command, if I get my boot.py file, this is going to print it out. So you can see it has right here import WebREPL and WebREPL.start, and these are uncommented. So there's no pound sign in front of them. That's a comment. So you want to make sure that your boot.py looks like this in order for the WebREPL to start and to be running. So make sure that you do that. And then to connect the WebREPL, I've done a whole video on this, but basically there is a MicroPython WebREPL page that you need to access. And you can actually access this from the MicroPython website. Now your computer needs to be connected to the Wi-Fi network that your ESP8266 is advertising, and my computer is connected. I just checked. You can't see it, but this is an iMac that I'm using that has Wi-Fi, and luckily it also has an internet connection through the Ethernet port, and that's how I can stream and be on the Wi-Fi network here. But I'm connected to my board, and so when I'm connected to my board, and if I connect and I click this connect button, it should connect to my ESP8266, hopefully, although maybe it's not connecting here. Let's see, let's disconnect. Let's try this again. So, let's reload the web page. Sometimes the web REPL is a little finicky, I've noticed. So we'll see it. Oh boy, this thing is really mad. Okay, let me reset the board, and then let's reload the web REPL page. So in theory, everything should be okay now, and then let's try to connect to the web REPL. There we go. Okay, so hey, sometimes things are a little bit weird. I've already connected before, so it saved this password. My password is Python, so you can go and connect and hack my board. Okay, so now I'm connected to the web REPL. You could use the serial REPL if you wanted instead of the web REPL. You don't have to use the web REPL. I just figured let's start out with the web REPL here. Okay, so NeoPixels. The basics for using these, I think I've shown this before in a lot of different videos, but basically you want to import the machine module and then import the NeoPixel module. And then once you have that imported, and let me see if I can increase the font size here. Let's see that. There we go. A little bit large, I guess. Let's go down maybe a little bit. Oops. There we go. That seems a little better. Okay, so I've imported the machine module and the NeoPixel module, and then I need to create an instance of the NeoPixel class inside of the NeoPixel module. And this needs to take in the pin that's connected to the input line of the NeoPixel shield. Now the NeoPixel featherwing. For the featherwing, you actually have to solder on the back. You can pick any of the digital inputs that you want. So for this board, I've used the digital input number 15 on here. So I want to do machine.pin 15, and I want to make this a machine.pin output. And then after this, I need to tell it the number of NeoPixels, and there are 32 NeoPixels for the feather wing. It's has 4 by 8 pixels, a little grid of them like that. Okay, so I do that. That creates my NeoPixel object. Now I can call fill, and this will set all of the pixels to a single color, and you pass in a tuple, a 3-tuple with the RGB, the red, green, blue values. So if I want to set these all to red, I can set this, and basically your maximum value is 255. It's a byte, an unsigned 8-bit value. So 255 means maximum intensity for the red component. 0 means no intensity for the green, and then the blue component right here. So when I do that, nothing happens because you have to call np.write. But basically that fill command will change the buffer internally just on the MicroPython board, and then the write command will take that buffer and send it out to the pixels. So I do that, and hey, everything turns on, and you get a nice red color like that. So, okay, cool. And then if I want to clear all the pixels, I can just set them to 0, 0, 0, and then write that out. and turns them all off. So everything's all good. Okay, so that's the basics of using the NeoPixels. Now I'm going to disconnect from the web REPL right now. Again, I just wanted to kind of show the web REPL, and eventually this is how I'm going to control this thing remotely. But I'm going to use the AMPI tool to develop a script on my computer here, send it over to my board using the serial connection. I think it's a little bit faster of a development process because I can write a script on my computer, and then once it's in a good state, I can save that script as the main.py file on my board, and then that will always run when the board loads up. Whereas if I did something in the web REPL, as soon as I power down the board, it's gone. Like I better make sure I remember exactly what I typed into the web REPL. So that's why I like to do things in a file and then send that file to the board to run it. So let's just do basically that code again. We'll import machine, we'll import the NeoPixel module. Let's save this as, let's call it lights.py. So this will be our main lights script. And again, let's make that NeoPixel object np equals NeoPixel.NeoPixel class, and machine.pin15 as a machine.pin.output with 32 pixels. Now I'm going to be a little bit smarter though, because, hey, I know for sure I'm going to change the number of pixels, 32, because, I'm just developing and testing against this little feather wing that only has 32, but eventually I'm going to go to that long strand that has like over 100 pixels on it. So I want to be able to tweak this value. So I'm going to make it a constant, or not really a constant, but a global variable. And in Python, the convention is your constants or your globals that you generally don't change are all in uppercase. So I'll put it up here and I'll say my pixel count equals 32. So that's where I put that magic value. And then it's just a little bit easier. So now later on, 3 weeks from now, when I've totally forgotten how this script works and I need to change these colors, I can just open this file up and know, oh, okay, yeah, here's where I have the number of pixels defined. I don't have to go searching through the whole script to figure out, oh, this magic little 32 value that I put here is that count. And same thing I'm going to do for the pin. I'm actually going to pull out this whole thing right here, and let's make a pixel pin object that I set up here. And so this way, it's a little bit more clear to me now that if I want to change, like if I hook up my strip of NeoPixels and I don't use pin 15, well, it's easy. I can just adjust right here which other pin I'm using. And I figured I would break out the whole pin object here because on other boards, like maybe the SAMD21, for example, you might want to use that board. It has a different structure for creating the pin object potentially. So this way, I just know that the NeoPixel class needs to take in a pin object. How that pin is defined, it can be board specific. So for the ESP, it might look like this. For a different board, it might be different. So this way, it's a little bit more clear that these are the things you want to change if you're moving this to run on a different board or like a different number of pixels. Whereas everything below this is probably the main code that in general you don't want to touch. Okay, so when this thing starts up, let's have it turn off all the pixels. So I'm going to fill with a value of 0. And this is just smart so that, when I run this script, it's just going to clear everything and just make it all stop. So that if something bad was happening, it's hopefully, or at least if I want to clear everything, I just run the script and nothing's going to happen initially. And then just to make sure that this file runs, let's put in a np.fill. Let's make, how about green? We'll set all the pixels to green and then np.write. Okay, and so now to run this script, I'm going to use the AMPI tool, and so I'm in this directory. You can see here's that lights.py file that I was just editing right here. And I'm going to use the AMPI tool, but before I use AMPI again, I'm going to set the AMPI_port environment variable. I'm going to set it to the USB serial port, or the serial port for the USB to serial converter chip, which for this board is this Scilab's USB to UART device. So because I set this environment variable, now I can just run AMPI ls or AMPI run or any of the AMPI commands, and instead of having to provide this port parameter, it's just going to pick it up from this environment variable. It makes it a little bit easier so that I don't have to constantly type that port parameter all the time. Okay, now if I want to run that light script, I can just say AMPI run lights.py, and I do that, and hey, look at that, everything turns green. So that's good. That's exactly what I expected. It ran this script, and when the script ran, it initialized the NeoPixels. It cleared them, which we didn't really see because it instantly cleared them, and then immediately after that it set them green. So let's just delete this and let's run it again to turn everything off as we develop this. So, okay, cool. So that's working. Now let's do some animation here. So let's go back to that Techno Tiki project, And if you look at the guide, I link to the code for it. It's in this Arduino repository. And you can see I have two versions of this. I have one with an infrared remote control that lets you switch the animations, and then one that doesn't use the remote control. Because I figured I'd make a version if you didn't have the remote and you just wanted to hard code, one specific animation, and you didn't want to add that extra infrared receiver and all that stuff, then you could do it. It's no problem. So let's start with that simple no remote control version of this code. And so this is an Arduino sketch. It's not MicroPython, so I'm not going to be able to take this directly and run it on this board. But we'll see. It's going to be pretty easy to port this over. So the way this code worked, basically in the setup, it just initializes the strip of NeoPixels and clears them, which is exactly what I'm doing right here, basically. I mean, if you want to think of it, like here's my setup code below here, and then my loop code, well, we'll come back to this because we kind of have to create the loop code ourselves. Whereas in Arduino, you have a loop function that you fill in, and it's just constantly called over and over by the way Arduino works. In MicroPython, you don't have that. You just have a script, and it just runs. And if your script doesn't have a loop in it, it's just going to run once, and it's done. That's it. And sometimes you want that. Sometimes you don't, though. So it's nice that you have the freedom to do both. And I'll show you how to add a loop in this example so that, when you want something to run forever, you can put an infinite loop into your Python script, and you'll get this Arduino-like behavior. But it's nice that you're not forced into always doing that, because maybe you just want something to run once, like a quick little thing that runs, does something, and then maybe like goes to sleep. And then at some point, the chip wakes up and then, starts and runs all over again, resets itself, something like that. You've got all the capabilities to do that. Okay, so the way that this code works, basically, it will loop through all of the pixels, and then you can set which type of animation you want, and it uses this switch to figure out which case. So there's animation 0 and animation 1, and if you go up to the top, I kind of describe, okay, animation 0 is a solid color pulse, which is not the best description in the world, but basically that will take every pixel and pulse between, it will basically, so you have a list of colors that are defined right here, and so this list of colors, this has 8 colors inside of it. And it basically, for every step through time, it will go through each color individually. So the first time step, it will pick this first color, and then it's in the next time step, it'll pick the next color, and so forth, through each step of time. Now that the actual length of each time step is defined by this speed milliseconds parameter, which speed is not really the right term for this. I should have called this period, because it's a period of time, basically. And so this is the number of milliseconds that it will spend inside each of those time intervals. So the default configuration here is 100 milliseconds. So when this runs, it's going to spend 100 milliseconds in this first color. And then after 100 milliseconds, it's going to switch to the next color. It's going to stay there for 100 milliseconds, and it's going to switch to the next color for 100 milliseconds. And in animation 0, the solid pulse animation, every pixel will be lit up that same color. So in the first step, everything is red for this color. This FF0000, that's a red color for this animation. After 100 milliseconds, every pixel will change to the next color. So this FF24, so that's like red that's slowly turning into a yellow color, if I remember correctly here. So that's how that first animation works, the animation 0. The second animation, I called this the moving color pulse, because basically this will take every pixel and it will map colors to pixels. So the first pixel will get the first color right here. The next pixel will actually get the next color, so it won't have that first color. The third pixel will get the third color, and so forth, all the way on down the line. And then basically every time interval, it offsets which color it's picking by 1. So it effectively looks like you have this train of colors that's just moving across your whole strip of pixels. And so this one's more of an animation where you see like movement, whereas the 0, the solid pulse, the solid color pulse animation is really just every light changes, and it's good for like going up and down in colors. Everything turns green, everything turns red, for example, for like Christmas colors, or like maybe Hanukkah colors. Everything turns blue, everything turns white. Whereas the moving color pulse looks more like if I had a red and green color gradient, or like a red and yellow color gradient, I would see moving across my pixels that red and green color gradient, and just slowly, constantly moving across that whole strip, just in a constant circle like this. So might not make much sense as I'm talking through it, but let's implement it, and then you'll see exactly what this thing looks like. So let's first implement the animation 0 right here, which is that solid color pulse animation. And the way that this thing works is basically it figures out, okay, for the current time, based on this millisecond tick that Arduino gives you with this millisecond function, I basically figure out, based on my current millisecond time, which color should I pick? So, I know that there are 8 colors that are available, and every 100 milliseconds I need to swap between the next color. So if I divide my current millisecond tick by my speed, or my time, my period in milliseconds, then that's going to give me basically an index into, or at least a count of how many of these 100 millisecond intervals have elapsed. And then if I use the modulus operator, then that's kind of a good way to constrain that value, because that number of intervals could be more than 8. That could be more than the total number of colors right here, which would be a problem because, if I got a value of like 10 and I try to index into this list of 8 values with an index of 10, it's going to go past the bounds of that array. And luckily in MicroPython, you'll get an error. It'll throw an index or a bounds error that says, hey, you're trying to access memory that you don't think you own, or that you don't actually own, and it will fail. In C and in Arduino, it will actually happily go read memory that you don't technically own. You might get a good value, you might get a bad value. Things might crash if you're lucky, or maybe they run erratically. Anyways, long story short though, I need to make sure that that number of intervals, which is what I'm using to drive this animation, never goes beyond the maximum number of colors, like this, this last color right here. And if it does go beyond that, I want it to wrap around basically, so that, if it goes 2 beyond this last value right here, well then actually it should go like to the second value, it should go back to the first value and then the second value right here. And the modulus operator, which gives you the basically the remainder after an integer division, gives you this kind of behavior. Like if I take any value modulo 8, then it's going to give me back a value that's the remainder if I took my value and divided it by 8. And, remember, like the way division works, your remainder can never be more than 8, because if it's 8 or more, then you would have gotten a larger value from the result of your division, and your remainder would then be like 0, for example, if you got like an 8 value back. So that's one kind of neat property of the modulus operator that you see used a lot. It's a good way to constrain a value to be within some range and to wrap around, so that if that value goes, maybe 10 values beyond the end of your range, the modulus operator will actually make it wrap around so that it appears as if it wrapped around. Like let's say I had a range of 8 and I gave a value of, how about 18? So like more than double through that range. 18 modulo 8 will actually give you a value of 2, which says, okay, you can divide this thing by 8 twice, so that gives you a value 16, and then a remainder of 2. And so it's that 2 value that I care about, because that 2 tells me, oh, I want the second color inside of here to index into this value. And so that would be as if, if I went 16 times through this this list of 8 colors, so 1, 2, 3, 4, 5, 6, 7, 8. So there's 1, 9, 10, 11, 12, 13, 14, 15, 16. That's twice through that range of colors. And then 17, 18, boom, there it is, my second value inside of there. So that modulus value is going to give me this index effectively here. So that's what this code does right here. You can see this percent operator, that's the modulus operator. So I'm basically just saying, okay, now in this animation, I'll show you this code is actually a little more complex than that, because the way that this code works, I actually look through my colors. I treat this as a ramp of colors, where this is like the colors that go from red up to yellow. So this first color right here is red, and this last color is yellow. Everything in between is all of the intermediate colors to get to that yellow color. But the way this animation works is it actually will ramp up through these values, and then it will ramp down. So it will smoothly go from red up to yellow, and then yellow back to red, and then start over, red up to yellow, yellow up to red. So it basically just ping pongs back and forth, You know, it goes forward through this list of colors, and then it goes backwards through this list of colors. So that way, in this configuration, I can just make this list of colors that goes one way, and then my code will make it go both ways so that I get a nice smooth gradient of colors as I go through here. And so that's where a lot of the complexity of this function comes from, in that I'm figuring out so that my range of colors is not actually the total number of colors in this list. It's actually the total number of colors times 2, but then minus 2 because I don't want to repeat the ending color twice. And I don't want to repeat the starting color twice because, you know, you'd see those for a little bit longer. So I cut those out, and that's why you see this kind of minus 2 right here, because I pull out that starting and ending values, and I don't repeat those values twice. And so that's some complexity. I'll show you how we can do this in MicroPython and actually make it a little bit simpler so that I don't have to do that kind of crazy logic in my code. Because effectively, I just want to mirror those colors so that, you know, if I want to ramp up my colors, I can have a ramp of colors that goes up, and then I could just tell my MicroPython code, by the way, go ahead and generate a ramp of colors down, you know, so take my ramp of colors up and just copy it and reverse it and, you know, make this a ramp that goes up and down in that case. And the nice thing is with MicroPython, I can do this all dynamically because it's just an array. You can dynamically create arrays. You can do all that in C and C++ and Arduino if you really want to. It's a lot more painful though. You know, there's a lot more things built into MicroPython that'll make this easier. But anyways, that's what this logic is doing right here. So this little check right here is looking to see if I've gone halfway through my list of colors. Then I know I'm starting to ramp down. And so now I need to start decreasing my values. I'm not going to explain this in too much detail more because, like I said, we're going to see this a little bit simpler in the MicroPython code. And then the next thing right here is actually just doing a lookup of the color data right here. It's using this pgm read dword near. This is because this color data is actually stored in the flash memory of the Arduino Gemma chip because I didn't want to store this in RAM. And so when you store stuff in flash memory, it's using this progmem thingy right here. You have to do this lookup to say, okay, go read this dword near your, you know, that's stored in your flash memory. Nice thing is with MicroPython, I don't have to do that. Everything is actually stored in flash memory. There's no concept of this separate flash memory store. So whatever I have in my code in my script right here is in flash memory. I don't need to do any special thing here. So if I want to define a list of colors, I can do it in my code right here. So and actually let's do that. So let's make a colors list, and I'm gonna make this just how about some global state that I set up at the top here. So we'll just say global state, and let's make a list of colors. So like I said, you know, this list right here goes through these red, yellow colors. Since this is holiday related, let's make this red, green colors, or how about red, blues? You know, I don't know of any holidays that use red and blue as their colors, but hey, we're gonna make a new holiday now because, you know, you might be celebrating all kinds of holidays, so I don't wanna give preference to any one holiday. Okay, so let's just do a quick little ramp from blue up to red. And so in between, you'll get like a pink color effectively. So let's go from 0, 0 to 255. So this is my starting color. So I'm making a Python array. So that's what this, you know, this square bracket notation is here. And inside of this array, I'm going to have tuples, a 3-value tuple, which is the color data that my NeoPixel functions expect, like the fill function. So I'm just going to have a list of colors in here, effectively, the RGB values. So my first one is blue. My ending color I want to be red, so that's 25500. And then let's fill in some intermediate colors here that go in between that range. So let's go like, how about 16, 0, how about 128? So we'll just kind of cut things in half as we go with this. So, you know, I cut my blue value in half, but then I just added, I started my red value at 16. And then let's kind of keep going with that logic. So I'll double my red value, so I go to 32, and then let's cut my blue value in half again, so I go to 64, and then let's go and let's double my red value again, and let's cut this in half again, and then let's do the same thing, so I get to 128, and then I get to 16, and now I can follow my logic. Okay, so now I've done 1, 2, 3, 4, 5, 6. So I've done 6 colors here effectively that just go from pure blue to pure red. So pretty simple and straightforward for these colors. But this is nice in that I've just defined my color values as a simple little array right here. Now let's make a function to do this solid color pulse animation right here. So let's make a function and let's call this solid. And for now, let's not have it take any function or any parameters in. We're just going to have it operate on these global values that it has up above. And maybe we'll come back later and adjust these functions so that they don't necessarily have to use this global state. Because now since I'm going to use these global variables inside of here in my function, I have to keep this function defined in this script file, which is not the best thing in the world. Like, you can imagine I might have like 100 different animation functions. I probably don't want all of those in one file, but if I want to pull this animation function out of this file, I can't do that if it depends on all this global state right here, because all of this state only exists in this file. So we'll come back later to see how to maybe pull this apart. But for now, I'm just prototyping, so I'm going to write this, and just use this global state. We'll get it working, then we'll kind of optimize it later for this. So okay, so let's do this solid color pulse. So the first step that I need to do is basically figure out, based on a millisecond tick, what is my current index into this color array? And based on some speed in milliseconds, or a period time in milliseconds that I was talking about. So let's add another configuration here. We'll say my period in milliseconds equals 100. So this is like basically the speed milliseconds value, or like I said before, speed wasn't the best name. I should have used period here because this is the length of time that it will spend in one color. And then, after that amount of time lapses, it will go to the next color effectively. Okay, so to get the current millisecond tick on the ESP8266 right now, you actually have to use in the microtime, the utime module, there is a utime.ticks_ms millisecond function. This will give you back a count that increases every millisecond. So that's why there's the _ms. And the value of that count doesn't really matter. All I know is that it increases every millisecond. It will go up by 1. So this is effectively like the millis function in Arduino code. So if you see millis, you can use ticks_ms in place of it here. So, and then I want to get, here's my current position. We'll assign this to a value called current. And to get this current position, I just want to divide by the period milliseconds. So this is just like the Arduino code. I'm basically taking my current tick counter, dividing by my period in milliseconds here, which is exactly what you see right here. Now, one gotcha in Python 3 and in MicroPython, because MicroPython is just like Python 3, division by default uses floating point. So if this tick value, if this is, well, for this you're always going to get an integer value. For my period millisecond value, I know this is always an integer because I set it to be an integer, but what if I set this to like 10.5? Some integer divided by 10.5, this might give me a floating point value. Or, what if I set this to a value that's not a factor of a tick value? So like, what if I had this set to like 3? Something that's, or maybe not 3, how about like 7, like a prime number? Then I'm actually going to get a floating point result here. So my current index might be like 1.587. And if I try to look at position 1.587 into this array, I can't really do that. Like I can only use integer values here. Now the nice thing is, if you actually want to do integer division, which is the default in C in an Arduino. So when you see this divide right here, it's actually, well, it's not necessarily the default. It's the default if both of your parameters are integers. And it just so happens that this millisecond function returns an integer and my speed ms value is also an integer. So this is going to do integer division. So I'll never get like a 1.5 or a 1.7 or some intermediate value. In those cases, it rounds down. So I just get 1 as the result back from this. And that's the behavior that I want in my MicroPython code. I want to do integer division. And luckily, if you do divide in MicroPython or in Python 3.0 code, that will force integer division. So even if my period is a prime number, and so that, no matter what, any number divided by a prime number is going to give you some fractional value, it's going to just chop off that fractional part and give me the integer component for that, which is what I want, because that's what I want to index into this array of colors. And that basically just means that, if I'm halfway through a period of time, sure, the floating point division might be 1.5, But I don't really care. If I'm halfway through that first interval, I'm still within that first interval, and so I still want to get that first value right here, and so that's why I want the integer division. Whereas, once I get past that first interval, and once I get, to like a value of 2.5, for example, with floating point division, then I'll be in the next value, and I don't care how far into that value I am. That 0.5 doesn't matter. All I care is that I'm 2. I'm at the second position inside of there for that. So, okay, so I just want to make the point, though, that you do have to be really careful, especially when you're converting code from C and C++ to MicroPython. Anywhere you see division, think very carefully, is this integer division, is this floating point division, and which one do I intend to use? And be explicit in your Python code, because this will burn you many, many times. It's very easy to just throw a division in here and then forget that, oh, you might get a floating point value, and that might cause a lot of chaos for you. So wherever you can, be explicit about this. Okay, so this current value is basically going to tell me, here's kind of my current, how about, let's call this elapsed instead of current. So this is the number of period millisecond intervals that have elapsed effectively. Now this is not my index into my color array yet, because remember, this number of elapsed intervals might be longer than this color array. I need to use that modulus operator to wrap it around back to the start when it goes beyond the number of elements. So let's just say current equals my elapsed modulo the length of my colors. So this is basically the magic step that's going to take the number of elapsed intervals that are period milliseconds long and wrap that around so that it will always fall within some range that I can index into this color list with. So, after just one 500 millisecond period, it's going to pick this first value, or within that first 500 or 100 millisecond value rather, or period ms, sorry, let's set that back to 100. After that first, up to that first 100 millisecond period, it's going to be getting this value of 0. After that, after, like, let's say my ticks millisecond returns 242 or something as a value. So 242 integer divided by 100 will give me a value of 2. Not 2.42, but 2, because it just gets rid of all that remainder. It ignores it completely. So I get a value of 2, and that's within the range of bounds for my list of my total number of colors. Like, that's less than the length of the color list, which is 5. So 2 modulo 5 is 2, because you're basically, 2 divided by 5 gives you a value of 0 with a remainder of 2. So that's going to give, it will keep my 2 value. But let's say I go beyond this, and let's say my ticks millisecond is like, 1200. So 1200 divided by 100 will give me a value of 12. So I'm 12 intervals into my animation loop effectively. Now 12 modulo 5 is actually going to do 12 divided by 5, which is 2. And then what's the remainder left? Well, that's 2 times 5 is 10. So 12 minus 10 gives me a value of 2. So the 12 modulo 5 gives you a value of 2, because that's the remainder of the integer division. And that's perfect. That's going to tell me, okay, I want to get, my second item inside this list of colors here. So that's, long story short, I've had all this exposition, but again, this modulo operator is really just wrapping around my current elapsed count so that it falls within this range of color values for this. And so that's what I can do now. I can just say neopixel.fill. Let's go, we'll index into that colors array with the current color. And then, oops, I don't want to put a 0 there. And then let's do the neopixel.write function, and that's it. So that's all that this solid color animation has to do. Okay, let's fill in the setup code, and actually let's fill in our loop code now. So let's I'll just restructure some things a little bit. We'll say animation functions, and then let's put our setup code below this right there. And then let's put our loop code here. Okay, so like I said before at the beginning, you don't have a loop function in MicroPython, but you can make one really easily. So just while true, this is an infinite loop. So once my code gets to this point, it's going to run forever. And in this case, let's just call my solid function. So I'm just going to have it always do the solid color animation. I'm going to do one other thing. I'm going to do utime.sleep. and I'm going to have it sleep for 10 milliseconds. And the reason I'm doing this is because usually you want to delay for a small period of time, especially on chips like this ESP8266. You need to sleep for a little bit of time so that because this is just a single core and all of your stuff is kind of effectively running bare metal. There's no operating system that's multitasking on this device. But on the ESP8266, it actually needs some time slices to give to the Wi-Fi radio and things like that. And so the sleep function is what you need to call to basically say, okay, in my main loop, I'm done running my code. Go just delay for 10 seconds. And while it's delaying, it's actually doing things in the background. So it's usually smart in your loop to have a small bit of delay inside of your loop. If you don't have this delay, sometimes your chip can just effectively lock up, or it feels like it locks up because only your code is running. This like solid color animation would run. And I'm starving everything else. Like the Wi-Fi radio might not be getting any time to run. Other processes on the ESP8266, it has a little real-time operating system. Those might not be running. So usually you want a small delay. It kind of depends on your board though. Like if your board doesn't need to have anything running in the background, then maybe you don't need that delay. But it usually doesn't hurt here. And the nice thing is the way that I've made this function work, because it's calling this ticks millisecond function, it really doesn't matter how much time elapses in this loop, because this ticks millisecond function is only going to increment every millisecond. So, you know, even if this takes longer or less than 1/10 of a millisecond, it doesn't matter. This ticks millisecond function is still going to increment at the same rate, no matter what in my code here. So, okay, so let's save this and let's run this code. So, now if this works, I should basically see it go through each of these colors and spend 100 milliseconds at each color. Actually, let's increase this to 500 milliseconds, my period, so it just spends a longer amount of time. So I should see it start blue and then go 5 colors up to red. And then once it gets back up to red, it should snap back down to blue. It's not going to gradually step back down to blue. We'll see how to add that logic in a second here. But you know, just remember, it's just going to loop through these colors in order like this. So let's do ampy run lights.py, and this is going to take my script and tell it to start running. And so now you can see, okay, so let's watch what this is doing. You can see it's, you know, it goes from red to blue, and then blue, and now it's kind of going through pink up to red, and then once it gets to red, it snaps back to blue, and then goes up to red again. And so you're basically seeing that logic here. So here's blue, so boom, there's the blue starting point, and then it just goes color by color. So the next color is a, you know, bluish pink, and then this is a less blue pink, and then this is like maybe an almost perfectly pink color, and then this is a more red pink, and then the top color is red, and so that's where you see red. And then you see when it goes from full red to blue is when it wraps around to this next color, which is blue, the bottom color here. So, and that's because of that modulo operator right here. So my index got beyond the last entry, and so it snapped back down to the first entry effectively here. Okay, so that's working, but this is not exactly how the Technotiki color project worked, because remember, the Technotiki, like I mentioned, it would go up through the colors, and then it would go down, so it would smoothly go back down through the colors. And I did that because I didn't want to have this break like you see. It goes up to blue, and then from blue it goes boom, right back down to red. I wanted it to step back through the colors in this case. So really easy way to do this in Python is I can actually say, let's mirror the colors to ramp down again. So basically what I want to do is I want to extend my color array. So there's an extend function on arrays in Python, and the extend function will just take an array and tack it on to the end of another array. So if I basically, what I want to do is I can say, I'm going to take this array of colors and I'm going to copy it onto itself again. So I'm basically going to do this, but I'm going to reverse it. Instead of copying it in order, let's copy it in the reversed order. So I can't easily do that with copy and paste. I'm not going to manually type this in. But luckily in Python, they have a reversed function, which is, reversed. Super handy built-in function. You just pass it a list, an array, an iterable, anything, and it will reverse it. It will give you those values in reverse order. So if I pass in colors reversed, then basically I'm going to take my color array and I'm going to take it as is, reverse it and add that to the end of it so that now it will double the size of it. And so now it's going to step up through the colors and then step down through the colors again. So let's save this and let's see how this changes it when I run the code again with this. So now it's going up to blue, and now you see it goes down to red, and now it goes up to blue and down to red again. So that's cool because basically, but you know, again, notice I only defined this ramp of colors from blue up to red. So this line right here is actually copying that and flipping it so that now it ramps up and down smoothly. But you do notice when it gets that blue color, it stays there twice. That's because when it copies this and reverses it, you actually get, or like the red color at the end here, you get that red color twice. And that's what I actually had all this extra logic in the Techno-Tiki torch to avoid, because really I want to get the second to last color after this. So that now it goes, you know, from this reddish pink to fully red, back down to reddish pink again, instead of fully red for a second go. Luckily, this is really easy to do in Python. I can use the slicing syntax to say, okay, from this reversed list of colors, don't pick the very first and the very last entries. Skip the first entry, which is actually the very last entry, because remember, it's going in reverse order. Skip the first entry and grab everything up to, but not including the last entry. So basically, slice off the beginning and the end entries and just pick that middle value. So it's really only going to grab these middle values right here in reverse order. That's exactly what I want, so that now this list of colors will smoothly ramp up from all the colors, but not double up the end colors. So if I save this and if I run this, now it's going to look really similar, but we won't see, hey, reversed object not subscriptable. Oh, that's cute. That's interesting. Interesting. So I was doing this a different way earlier. So, okay, so I'll show you how to fix this. Basically, I need to tell it to make a list out of this reversed thing. So this is the result of this reversed function in Python 3 gives you an iterator. And to slice into an iterator like this, sometimes you can't do that. So this list function basically says, okay, go make a new list in memory, and then I can slice into that. So this is, yay, you're watching how to debug things live with this. Okay, so now this is actually working the way I expect. So you can see it gets up to red and it gets down to blue, but it doesn't stay there twice. It's skipping those end results. And so this is actually now behaving exactly how the Techno-Tiki project would behave. And if I want to change this, you know, I can just change like my period milliseconds. This should speed it up. And so if I run this, now you'll see it's going to run a little bit faster. So boom, you know, it's going through the colors, and it's only spending 100 milliseconds at each color here. So, okay, so that's cool. So, you know, that's the basic animation stuff working here. Let's do the next animation function here. So this one is really similar to the previous animation. The only thing is I just set each pixel, when I compute kind of the current position into my colors, I offset it by my pixel position. So let's just look at the code for this. So I'm going to make a new function for this. Let's call this, I'm going to call this chase, because this is kind of like a theater lights that chase themselves through, you know, it looks like they're moving. That's effectively what this is going to look like. Now this function is going to be a little bit different because I can't use this fill function because this sets every pixel to that color. I actually have to go through pixel by pixel and set its color because each pixel is individually set to a different color. Now the elapsed time, or like the elapsed interval, and the current index into my well, actually no, the elapsed intervals I can use, but I'll show you I actually need to compute my current index in a slightly different way. But first let's loop through all of my pixels. So we'll say pixel counts, so for I in the range of all of my pixels, and then now to set each pixel, you index into the NeoPixel object like this, and I can set each pixel to a color. Now to figure out the color for this, let's actually, before I set the color, let's set that current index to elapsed modulo the length of my colors again. But here's the difference. So this function right now is exactly the same as the function above. Well, actually here, if I set my colors current, and then let's add the NeoPixel.write. Okay, so this implementation is exactly the same as this function right here. Just instead of using the fill function, I'm just looping through each of the pixels. But here's how I'm going to make it chase. I'm going to take that elapsed value and I'm going to increment it by the current pixel position so that each pixel is going to get the next color. And then because I'm doing this before I do the modulo length of colors, it's going to make sure that I wrap around correctly so that, you know, as my number of elapsed time intervals changes and my current pixel position changes, it's going to loop back around and make sure that I'm always within this range of color values here. So, okay, so let's save this and let's change my code to call the chase function instead of that solid function. And let's see how this works now. So when I do this, and okay, so now this looks a little bit different. So you can kind of see, it's maybe a little bit hard to see because the camera is kind of auto exposure, so it's a little bit bright. But basically, you can see it looks like the array of colors is kind of moving, and so the way that this NeoPixel Featherwing is set up, it's really just one long continuous strand of pixels, even though it's set up in a grid. So you can see it starts from the top right here, it looks like, and the colors kind of move in and then move down like that. So you can see like a red color comes in and slowly moves across the whole thing. You know, it's moving down that position. And it's basically just, you're seeing this list of colors moving or chasing itself across the entire strip of pixels. But it's not just this list of colors, because remember, we're doing this little magic to mirror so that it ramps up and ramps down. So you're seeing that ramp up and ramp down moving across your whole list of pixels. And so this is kind of cool. This is nice in that, you know, if I wanted to do a nice like green and red, like Christmas color animation, and I had this, you know, wrapped around the wreath, then it would look like a green and red little set of colors moving across the wreath as I went with this. So, okay, so this is cool. Let's see. So we've got our two animations, and again, this is exactly what the Techno-Tiki would do. And with the Techno-Tiki, though, it was fixed. Like, you just picked your animation ahead of time, or you use that little infrared remote control. Now, we're going to make this a smart project. So, you know, right now, it's kind of smart as is. So let's comment out my loop, and let's save this. And let's put this on my board. So I'm going to use ampy put lights.py. And now if I do ampy ls, now I have this lights.py on my board as a file. You can see right here, here's that lights.py on here. Now let's go back to the web REPL and let's connect again. And hopefully this thing connects. Although I've noticed, you know, sometimes I have to restart the board and the web page here. So let's try this again. Hopefully it connects. There we go. Okay, so Python. Okay, so now I copied over that lights.py. I can import that lights.py by just running import lights. And you can see it just turned everything off, because when it imported that script, it actually ran my setup code right here. Now I commented out my loop code because I don't want this thing to jump into my loop, because once that loop is running, I can't really use the web REPL anymore. I actually have to press Control-C to stop the loop from running. But these functions are still defined right here. So if I want, I can call chase and say, okay, you know, run the chase animation. Oh, actually, sorry, I can't do that. I have to call lights.chase because I imported the lights module, and Python is smart. It won't actually pull all of that into the global namespace. I have to tell it in the lights module, call the chase function. And so that's what this is going to do when I do this. And so now it's doing this, and interesting, it's, oh, sorry, duh. So this just ran one iteration of the chase function. I guess I have to make this loop myself. I forgot what I was kind of doing here. So if I want this thing to loop, I can write my loop in my web REPL here and say, okay, lights.chase, and then, I don't know, let's see what happens. I'm not going to call the time.sleep. This might be a bad idea. I might lose control of this thing. But let's let this thing run. So okay, so it's running right now. It's doing the lights.chase, but you can see like I can't do anything in my web REPL. If I press Control-C, let's see if this breaks it out of it. Okay, it does break it out. Oh, and you can see that's when I just typed on the keyboard. It put a bunch of junk in here. Oops, let me go back to delete all this stuff. So, okay, so you can press Control C and I can stop the loop. And if I wanted, I could run, instead of the chase, I could do the solid animation here. So, this is kind of a smart web-controlled holiday light thing. It's not the best web control in the world. You have to type in code. I'm not pressing a button, but this is kind of cool in that, this through the web REPL, I'm just calling these functions and running a little loop that I have here to make this thing work. So, okay, so let's make this a little bit easier though. I'm gonna press Control C to stop this, and actually let's disconnect from the web REPL. Let's make it so that I can pick which animation I want to run in my main loop here. So let's see. And I'm just trying to think through how I want to do this, because I've done this a few different ways. So I could have this set up as like a variable that you set, like, what is the animation that you want to run? Or maybe I could make a function that I call that says, okay, run my animation loop, but use like the solid animation function or the chase animation function. Maybe that's what I'll do. So let's make a new function here. Let's call this about run. How about animate lights? Let's call this animate lights. And this will be my main loop. And let's have this take in the animation function to run. So we'll have it take in a parameter called animation. And let's just have it basically be this loop that I commented out here. So we'll have it jump into a main loop while true. And let's have it call this parameter that was passed in. So the nice thing with Python, you can just pass a function as a parameter and call it. So when I call animate lights from the web REPL, I'm going to need to pass in either solid or chase. I'm going to need to tell it which function to call. And then let's also, we'll give it that delay inside of here. So we'll say utime.sleep 0.01, even though it looks like maybe I don't need that delay, but I'm just going to be nice and do that in here. Okay, so I've got my animate lights function in here. Let's save that, and let's put this back on the board. So let's put my lights.py onto the board. And now let's reconnect in the web REPL, and hopefully looks like I need to reset the board, and then maybe it will connect. Let's see if this works. Connect. There we go. Okay, so Python. Okay, so now the way this works, I don't need to type in the loop anymore. I can just call, well, first I need to import lights, and you can see turn everything off. That's what I expect. And then I can call lights.animateLights, and remember you can press tab to autocomplete. And now I have to pass in which function I want it to use. So let's do lights.chase. And I don't need to call this, I'm just telling it the name of the function. So I don't actually pass in the parentheses and the parameters and things. So now when I do this, cool, so now it's running that animation like this. So that's kind of cool. And I can press Control C to stop this thing. If I want to change the speed of this, I can actually change the lights.period_ms value. And like, let's set this to 500. So this will be a lot slower. Well, if I want, I can see the current value is 100. But if I want to change this, I can say, okay, let's set this to 500. So now you can see this is 500 milliseconds in each period. And then let's run this animate lights function again. And now you can see it's a lot slower. So it's just, it's spending 500 milliseconds in each of the steps through the animation here. So this is cool. This is maybe getting closer to web control, where this is like the hacker web control. You need to know, yeah, I'm going to get in there and manipulate the variables and start calling functions. And, for me, this might be good enough. I'm on my phone and I know to type in lights.animateLights, and it's going to run that function and, run my little chase animation. Or if I wanted, I could change the colors also. So lights.colors. This is that array of colors, but if I wanted, I could actually go in and change this array of colors. Now this is kind of cool in that you can actually see this array of colors is showing me the value with the ramp up and the ramp down. So you can see, 00255 all the way up to 25500, and then here's that ramp down that it created. So you can see the ramp down values, even though in the code that we sent to the board, we don't have all those values in here. You're seeing the results of this color.extend basically here. So kind of cool that you can see that. But maybe I want to make this a function. So let's make this a function that's kind of a helper function. So let's say def about mirror let's just call it mirror. So this takes in some values, and it's going to return an array that has values, and then extended on to the end of those values, the reverse order values, basically this code right here. So I'm going to throw this into a function so that if I want, I can set my colors to be a mirrored value in the web REPL really easily by just calling this mirror function and setting that color value. So let's just take my mirror code here, and let's return value. Well, actually, let's have this return instead of extend. Let's have it do that. Let's do return values.extend, the list of values reversed, and then chopping off the starting and the ending values here. So I'm just taking the code that I ran before that only worked on my global colors value, and I just turned it into a function. And then so let's call that function at the start now. So colors equals the mirror of colors. Okay, so let's save that, and then let's go back and let's just disconnect from the web REPL again, and let's put that lights.py on the board. And so now if I reset my board and then connect to the web REPL again, it should hopefully connect in a moment. There we go. So we say Python. Okay, so now let's import lights. And now if I look at lights.color, I should have the same value. That's not good. I think I might have made a mistake in the file. So colors equals mirror of colors. Interesting. So this is not giving me the value that I expected here. I didn't do this ahead of time, so this might have been bad. But let's play through this and let's see what we're getting here. Oops. Let's go back to the web REPL. So let's just look at what's everything in the lights module. I just want to make sure that I'm getting the So the dir function will like list everything inside of a module, because I want to make sure. Okay, yes, there is that colors object in here. But if I look at lights.colors, what do I get? I get nothing back here. So let's call that mirror function. So if I call lights.mirror, and let's pass in 1, 2, 3, and let's see what I get back here. Oh, I get back nothing. That's not good. So something is wrong with how I define this function. So let's see. So my values.extend. Okay, so let's just debug this a little bit. Actually, here, let's go into the web REPL, and let's just make my mirror function in here. So we'll say mirror, and we'll say values, and let's just return values, and let's just do nothing with it. And so if I mirror 1, 2, 3, I should get back all the values. Okay, that works at least. So let's go a little bit further. So if I do my values, and I want to return, oh, I know why, because the extend function doesn't actually return your values. So this is kind of, it's not really the best. I'm kind of mixing two different kind of concepts here. So here's the thing. Sometimes you have functions that mutate the state of the thing you called them against. That's what this values.extend function is doing. I actually, when I call values.extend, it's changing this values array and adding on to it. But it's not actually returning anything. Whereas sometimes you get functions, and this is actually a little more common maybe in other programming languages, where this values.extend might return a completely new array of values. It won't change this values object. It'll actually create a new array that's set to your old array plus whatever you wanted to add to it. But that's not how Python works, but that was how I was assuming it was working there, and that's why that return was giving me no value. So this is actually what I want to do for my function here. So I'm basically saying, okay, take my values parameter that was passed in, extend it, doing all that magic to mirror and reverse it, and then return that value. So return that value that's been extended and mirrored effectively. So okay, let's save this. Let's disconnect from the web REPL. Let's push this back to my board, and now let's actually see, and I'll reset the board just to make sure that the web REPL can connect. And now let's connect to the board, and after a second here, we'll type in our password. Now if I import lights, now lights.colors, there we go. We get the values that we expect here for this. So Again, simple mistake, easy to make, that kind of thing. And it's, you need to be aware of, and it sometimes differs. Some functions, if they're really good about being consistent, then all of the functions end up mutating things, and none of the functions create new values, or it's the inverse. All of your functions will create new values, and they never mutate the state of it. It just kind of depends. There's, like some things are better in some cases, some things aren't. But you need to know how your functions work. So this is a problem when you switch between, I was just using some JavaScript libraries that don't mutate their values, and so it's easy to forget how your code works. Okay, long story short, the whole reason I did this is because now if I want to change my colors, I can say lights.colors equals lights.mirror. And let's pass in a new list of colors, and it's going to go and mirror those colors. So let's just do a few colors here. Let's say, how about 0, 0, 255? So this is like fully blue. Let's do 0, 255, 0. It's going to be green. And then how about 255, 0, 0? So that's going to be red. So it's going to mirror that. And so now if I look at lights.colors, I'm going to get blue, green, red, blue, blue, green, red, green, and then it's going to go back down to blue. So now if I call lights.animate lights, and let's do how about solid animation? So now you can see it's going a little crazy. So let's change my lights dot period milliseconds equals, let's set that to 500. This increases the amount of time. And now let's do this. And so now, now you can see it's going through, blue, green, red, green, blue, all through that mirrored list of colors. So again, this is Wi-Fi remote control of my holiday lights like this. And if I want to do a different animation, I can say, let's do the lights.chase animation for this. And so now you can see, and this is kind of cool, the way that it's stacked up. It just so happens the number of colors that it's looping through is a divisor of the number of pixels in a row here. So you can see that it's they're all kind of stacking up, and you're seeing columns of colors changing here. But that's kind of cool. This is how I can make my Wi-Fi or my smart holiday lights effectively. At least I've kind of prototyped it. So I think I'm going to wrap up this video. Again, I really just wanted to start this project. This is part 1. So in part 2, we're going to come back. I have right now all of the basic functions to run this animation. So I have 2 types of animation. I have the solid and the chase animation. I have a list of colors that I can change, and I can even ramp and mirror the colors in nice kind of easy ways. I've got a bunch of variables that kind of define the speed of this animation. And so just with all these basic building blocks, I have a loop function that I have here. With all these basic building blocks, I can connect to my web REPL and just call the Python functions and change the Python state and make this thing change its behavior, which is pretty cool. So the next thing I want to do, so here's the problem. When I reset this thing, it just so happens if I unplug this, well actually I just disconnected because I reset the board. If I unplug this and if I plug this back in, it doesn't do anything. It doesn't remember what was its last state. And so that's what I'm going to do in the next part. I'll start with how do we keep track of what color and what animation do I want to use? How do we save that on this device so that when it starts up, it goes back to that color and that animation that it was running? And so, for example, if I change it to do the solid animation at 500 milliseconds, for a period or something like that with a certain list of colors, I want it to remember that state and save it on the board. So when it starts up, it goes back into that state. And then I want to make it so that I can change that value from the web REPL, but also I want to be able to do this from a web page eventually. So that's, we'll get to that maybe in the next video. Maybe this turns into a 3-part one. But so that's the next thing I'm going to do in the next video is let's see how to take these basic functions and then add extra logic so that I remember which functions I last used, or have some ways that I can store, this is the function I want to run, this is the speed that I want to run at, and store that on my board so that when the board boots up or when it starts, it goes right into that animation in that loop. So that's kind of the building blocks for making a thing that, you know, I just plug in and I've got my lights wrapped around the tree or the wreath or whatever, and it's ready to go with this. So, okay, so I'm going to wrap this up. If there are any questions, throw them into the chat. And as far as the code for this goes, I'm going to put this into a gist and throw it up onto GitHub. So when this goes up on YouTube, I'll have a link to the gist. But you know, this is the code right here. And again, this is like halfway. This is not completely done yet. So this is maybe just a good little example if you want to use like these animation functions yourself. But for now, you know, this is in progress code. So we're going to build this as we go. So part 2, we'll look at how to remember this state and, you know, make it something so that I can set it in the web REPL and then store it, and so when it starts up it will actually go and rerun that state. And if you're curious how I'm going to do it, you know, maybe for homework, take a look at the UJSON module, the MicroJSON module. So that lets you serialize and deserialize JSON format data. And with JSON data, it's kind of nice in that I can take a Python dictionary or a Python array and save it to a text file in JSON format. And I can do the reverse. I can read a JSON text file and pull out all of the arrays and dictionaries as Python objects. So if you think about, you know, the state of my program is basically defined by like these parameters, these variables right here, my list of colors, the period in milliseconds that the time takes. I could save those into a file, and then when my board boots up, read that file and read the current values for like what is my period in milliseconds, what's my color list, which animation function should I use even potentially. So that's what we're going to do next time. We're going to see how to save that data. We're going to use JSON to do it just because that's a handy text representation that MicroPython has code built in to handle. And so we'll see how to do that in the next video. So, okay, so let's see. Let's go back up. Oh, so someone mentions, this is probably the problem I might have had with my 1.8.6 version of MicroPython. So yeah, thank you, Neurodoc in the chat. Basically, when you're flashing MicroPython to the ESP8266, if you're using the 1.8.6 version of the firmware, it sounds like you need to use the --flash_size equals detect option instead of explicitly setting it to flash size equals 8M. And that is actually, if you search for MicroPython ESP8266 flash, there's an old guide that I wrote that says how to do this. And let's actually edit this guide. So in this guide, I show how to flash the firmware to the ESP8266. And in this parameter right here, this flash size equals 8M, it sounds like we actually want to set this to detect. So let's actually change this. You know, this sounds like a good thing to update here. And I'll test this out right after this stream. But it sounds like this is what we want. Because usually I always forget all these parameters and I have to search for this page myself whenever this happens. And so this might have been what was tripping me up before. So thank you for that tip. But otherwise, let's see if, oh yeah, let's see, lots of things in the chat. Let's see, I'll go back up to the top and see what was in the chat. Let's see. Oh, someone was wondering how to learn Python. So yeah, there's a book that I've heard, I haven't read it myself, but I've heard everyone recommends it. Automate the Boring Stuff with Python. So I haven't looked at this myself, but I've heard that it's really good. And from what I understand, it's intended for people who know programming, like you maybe know a little bit about like Arduino or C or something like that, but you don't necessarily know Python. And from what I understand, this book is all about how to, you know, do the basic syntax of like how to loop through stuff in Python, how to create an array in Python, how to use a dictionary in Python, that type of stuff. But all in the context of like doing things, not these, you know, stupid toy examples of count the numbers 1 through 10. You know, that's not the most interesting thing. I think this has you do things like, oh, I've got a directory full of photos and I want to grab all of the photos that, you know, were created after a certain date or something like that. And so how do you do that? Like, how do you loop through files in Python, and how do you pick out certain files that match a condition? So I've heard really good things about this book. So you might check it out if you're trying to learn Python. And if you do have some understanding of programming, then this is probably a better introduction, because it hopefully glosses over a lot of like, here's what a loop does, here's what an if statement does. Let's say this book might be online for free. That would be kind of cool if it is. It looks like it might be online for free. So hey, check it out online. But it's, I find it's easier to read books physically sometimes. Let's see. Okay, yes, that's a book that I'd recommend. The other thing was Learn Python the Hard Way. So this is the tutorial, also free online, but also a book version. And this is a very comprehensive introduction to Python. And basically, let's see. Yeah, I'm pretty sure you can read it. Oh yeah, here you go. You can read it online for free. This goes through lots. I mean, you can see there's like 50 different sections here. And it has all kinds of, at the end of each section, it has you kind of test your knowledge. So you'll learn like what a loop is and how to do a loop in Python. And then you have a bunch of examples that you need to write to use that loop function. So I like this one because it really forces you to go through and learn everything about the language. But it might be a little too heavy, if you already know a lot of programming stuff and you just want to learn Python, maybe check out this Automate the Boring Stuff with Python. So, okay, so that was one question. Let's see. So cool. Yeah, I think that was about it question-wise. So, yes, it looks like. Cool, yeah, so I think that was it. So I'll wrap up the stream then. Let's see, I'll jump back to the main view on here. Oh, oops, and I've got the side views also. This is like triple camera. Let's see, where did the cat go? The cat, she's in the back, behind my head here. If I move over here, you can see this. Well, let's see if I, there we go. There is the cat. There's cat camera right there behind me. So sometimes she likes to go in that box back there. Anyways, thanks for watching. Tony from Adafruit. This was part 1 of the MicroPython Holiday Light project. So this will be at least 2 parts, maybe 3 parts. And again, the end result is I want to take this wreath and I want to take this strip of NeoPixels that are going to be wrapped around this wreath eventually. And I want to animate these things, and I want to make them controlled from a web page, like from my phone or from my tablet, from anywhere. And so that's we're doing the building blocks of that in this project. In this first video, you basically saw how to do animation. So I took that Technotiki project and converted it into MicroPython and just built some simple functions that I can put into a Python script, put it onto my Python board, my MicroPython board, and run from the web REPL. So over Wi-Fi, I can say, animate with the chasing color animation, use this list of colors, for example. So this is like the start, the building blocks for the next videos where we'll look at how to save that state of which animation I want to run, and then also how to control from a web page. And so that's going to be I think probably the most interesting part of this series, at least for me, because I always love to see what's the interaction between a web page and some physical device. So I'm thinking we'll hopefully be able to use the WebSocket connection that the web REPL page uses. I'm thinking I'll be able to build a web page that acts like the web REPL, but doesn't give me that REPL interface. It just bakes in and says, okay, you want to change the animation? Connect to the board like you're the web REPL and call this function to change the animation, for example. So I don't know, I haven't tried it yet myself, so we might see if the second and third videos in this series are a radical departure. Then I've probably found that it doesn't work and that maybe we needed a new strategy for this. But darn it, we're going to get these lights controlled through a web page one way or another with this project. So stay tuned for future videos. Check out youtube.com/Adafruit. You'll see this video and all kinds of other project videos on there. Twitch.tv/Adafruit. That's where I stream these things live. I like to do at least a couple streams per week. So usually on a Tuesday and on a Friday I'll do a stream. So Friday this week we'll do part 2 in this series. So we'll look at how to save the state and maybe hopefully get to how to control from a web page that's not the web REPL in this case. So until next time, this is Tony from Adafruit. Thanks a lot for watching. If this is useful stuff, if you like it, then click the like button, comment, let us know that this is good stuff and that it's interesting, and we'll keep making content like this. So until next time, Tony from Adafruit. Thanks for watching. See ya.